Okay, let's get going. Good afternoon. Welcome to today's I4Energy seminar. My name is Gaiman Yi. I'm the technical director of the I4Energy Center, and today's speaker is Dr. Igor Popotny, and I guess I'm sure most of you know who he is. I like this kind of a smaller, intimate group, actually. So Dr. Popotny is a research scientist with Citrus and also with the Berkeley Sensor and Actuator Center. He's also a member of the I4Energy Steering Committee. His research interest is in microelectromechanical systems, environmental and energy sensing, as well as microrobotics. Dr. Popotny has a BS and MS degrees from Arizona State University and a PhD from Dartmouth College. And I'm very fortunate to be working with Igor on several projects this year. So let's welcome Igor.
All right, thank you, Gaiman. Well, thank you all for attending my talk. And what I'm going to be talking about today, actually, is a concept that we have been working on in our lab for several years now. This is essentially using sensors and field-based sensors to monitor electric circuits. It's a theme that goes on through several of our projects. What I'm trying to do in this talk is actually bring it sort of together to a common theme, and that is, remote monitoring of electric circuits. So I will talk about some theory, and then I will actually show you and talk to you about the projects that actually involve some of these techniques. As Gaiman mentioned, I'm working in Citrus and BSAC. I will show work of several students in our lab. Specifically, the two that are working on this concept right now is Richard Su, who is in the audience right there, and then Christopher Sherman, who is right there. This work is conducted in the lab of Professor Dick White and Paul Wright. So, the brief outline of my talk is essentially an introduction of the concept and necessity for this proximity-based sensing. And then I'll talk about more sort of the concept, try to abstract and show you what we mean really by proximity-based sensing and why is it important, what are the challenges of this technique. And then I will move on to these two applications I mentioned, where you actually will see implementation of this technique in projects that we're currently pursuing. So, the concept is really simple. Basically, let's say we have a circuit, has some current and some voltages at these different nodes of the circuit. Because of that, there are some fields that are emanating from the circuit. We have electric fields and magnetic fields that are essentially emanating from the circuit. And if we would like to interrogate or measure what's actually going on there, as opposed to coupling, physically, putting a probe into these different terminals, we're actually going to put some sensors in close proximity to the circuit. And in these sensors, we're going to pick up these fields that are emanating from the circuit, right? So these sensors are not galvanically connected to the circuit. They're sort of distributed around the circuit, right? And based on the fields that these sensors are picking up, we can then infer something about what's going on in that circuit. That's essentially the goal, right? So you have this distributed set of sensors, and they're actually interrogating and measuring and investigating what's going on in the circuit. We don't have to limit ourselves. Before I go there, we would probably need to know, what is the distances between these sensors, so where they're distributed in space, and maybe the distance to the circuit they're measuring, right, to help us actually infer what's going on in the circuit based on the fields they're measuring. And we don't have to limit ourselves to these electric or magnetic fields. You can imagine that these sensors are actually measuring thermal gradients, right? Things like that. They're picking up radio frequencies, so high-frequency electromagnetic fields that are also emanating from the circuit, and essentially use all that to infer, what's going on, what's happening in the circuit, without necessarily having to have a physical connection with it. Also, another thing we might envision is that these sensors are actually actively interrogating the circuit, right? So they're actually sending signals that actively interrogate what's going on there. I'll show you an example of that actually later on, where that is very useful in some of the applications. Now, sometimes we might know what the circuit looks like, right? And so all we're looking for is the quantities flowing to the circuit. A lot of times we actually don't know how the circuit looks like. It's a black box, and we're interrogating it, right? We want to figure out what's going on in it. We don't really have a physical intuition to the geometry of the circuit. We might have maybe some idea, we might know there are some wires or some circuit breakers, but we don't really know physically where these wires go. So that's sort of the setting of the problem. And the reason that this is exciting, it allows us essentially to create these sensors that can be completely self-contained. And so in this case, this is a concept of the sensor that we're working towards in our lab, which is completely self-contained and allows and again can perform these measurements autonomously. So in this case, the sensor has a energy harvesting unit, some energy storage, a radio, and then these sensors, these proximity-based sensors that measure these electric and magnetic fields. And because there is no galvanic connection to the circuit, this sensor can be completely encapsulated from get-go, right? So that increases reliability and then allows this sensor to be placed non-intrusively either in legacy equipment, right? So I'll show you an application of this to circuit breaker panels. Or you can even imagine having this thing embedded in electrical equipment, but then you don't have to worry about the functionality of the circuit actually impeding the functionality of the circuit you're measuring, right? Because you're completely separated from the two. Okay, so that's essentially the concept. And then these are just examples of some of the sensors we're using. And I should also mention that we're currently only have been implementing this on current sensors, so magnetic field sensors. This concept applies also to electric field sensors. However, I will, when I go through sort of the theory of this, I will mainly focus on the current sensing aspects of it. The applications, of course, is if you think about energy monitoring in your home, and specifically energy conservation, you might envision these sensors essentially being connected to smart appliances, being part of a smart appliance, distributed throughout your home. And then because there are essentially no need for galvanic connection with the circuit they're measuring, they can be quite easily installed inexpensively. And then you can have this network throughout your home that helps you with, provides energy monitoring applications, helps you with energy conservation, and also monitors a demand response event. So this is essentially a technology that would enable easy and inexpensive installation of such networks in our home. The applications that I'll be talking about here are essentially the two top ones here. So I mentioned the monitoring of circuit breakers, so I'll be talking about that. Which allows us, without the need for an electrician, to essentially install a system that monitors the current in the individual circuit breakers. And then another interesting application that we're also working on and have been for several years is the diagnostics of underground power distribution cables. And the reason we need proximity-based sensing there is that we want to diagnose these cables while they're live online. And so we don't necessarily want to connect to the cable. We would like to do it remotely. And so that's another application. But there are many others. For example, an interesting application which I found, which actually has been published already in 2003, is remote investigation of or diagnostics of an integrated circuit die. So there are actually magnetic field sensors that are sensitive now, that they can do full-blown magnetic imaging of the currents that flow through an integrated circuit. So then again, you can now investigate what's going on in the circuit. You can imagine, almost an espionage application where somebody puts something like that onto an integrated circuit and can eavesdrop. But you can also diagnose, what's going on in my integrated circuit. Why is it not working? Why is it broken? But by the same token, an interesting application would be reverse engineering. In electrical engineering classes, we use SPICE a lot for modeling, and of course, SPICE was developed here at UC Berkeley. But what if we could take that device, this integrated circuit, the PCB board, put it into a scanner, and then scan the electric and magnetic fields emanating from that circuit, and then reconstruct the SPICE model out of it, right? Again, it should be doable and comparable to this. And so that then allows very quick, rapid reverse engineering and prototyping. So those are some of the applications, and this is why I think this technique is exciting, because actually it has a lot of potential also beyond this. So just looking at a higher level of abstraction, what does it mean proximity-based sensing for currents? So let's just assume that we have a system, and in this case, the system is, this is the boundary of my system, and there are several circuits or wires that are carrying electric current, right, in this system. And we want to really figure out a way to monitor this without touching the wires, right? And so, we can drop in some sensors, some magnetic field sensors, for example, like this. And this is, in this case, a planar system. Of course, this extrapolates to a 3D system as well, right? So we have this configuration space. And so we have a set of, circuits and a set of sensors. And so what happens is if we have this configuration, each of the sensors essentially senses the magnetic fields emanating from all the wires. And so what's happening is the way you can actually represent this is through the following matrix. It actually becomes a little bit clearer if we expand it out. But basically, this vector represents the output of each of these sensors, whether it's voltage or current or whatever, but it's a sensor output, right? And then these are the currents flowing through the individual circuits, right? The matrix in the middle, it's the sensitivity coefficient matrix. And that is the matrix that links the component for each of these currents to the individual sensor, right? And because of superposition, right, because the components of these magnetic fields will actually add up in the individual spot of the sensors, the output is actually going to be a sum of these individual contributions, right? Now, the sensitivity components will actually vary depending on the distance, right? So if the wire is really far away, there's not going to be that much magnetic field being picked up by the sensor. But in general, this would be the case. So, the question is, if we go back to the matrix form, how do we work with this? So, the sensor values, right? The sensor vector is what we get. That's what we measure when we look at our sensors. X, in this case, are the currents that are flowing through the circuit. Those are given, right? So we have X given. A is that matrix. And so the question is, how do we figure out what the matrix is? This is the problem of calibration, right? So if we know where these sensors are distributed in the system, if we know the configuration of these wires, then that problem is simple, right? We can just calculate it. We can calculate this A matrix, and we know what's going on. Now, if that's not often the case, so one way we can get at it is, for example, to perform a complete scan of the magnetic field in that system, right? If we do a scan of the magnetic field, we have complete knowledge of the field distribution in the system. We can then back calculate the geometry of the circuits, and then from there we can back calculate the sensitivity matrix. It's one way to do it. So one way would be to essentially have many of these sensors distributed, like a matrix. The problem is that that gets both expensive, and we also there is an issue with the distribution or the separation between these sensors. So if they're too far separated, you essentially have to make some assumptions about the configuration of the wires. So another way to do this is to essentially do a magnetic field scan of these magnetic fields, right? So that's actually one way that we have implemented a system like this in one of the projects I'll be talking about a little bit later on. Of course, there are special cases. For example, if we know that the wire is straight, there's one wire, then there is actually a case that we can place these two sensors. If we have a line that's perpendicular with the wire, so we know the location of the wire, we can actually place two sensors in known distance from each other, and then self-calibrate and essentially get the sensitivity from there. And this is something that actually Chris Sherman has developed and perfected in his MEMS-based current sensors. Okay. So that's essentially the the problem setting for this proximity-based sensing of current, and I basically will now proceed to describing two applications of this, and so some of this theory maybe becomes more clearer to everybody. But before I proceed, are there actually any questions regarding this? Yes?
How does the sensor or the array of sensors modify the existing electric field for the time?
That's a very good point. So with electric field, there could be a modification, right? In the case of the magnetic fields, there is none, or marginal, right? Marginal modification. So it doesn't change the system. It could. So with the magnetic fields, with magnetic field sensors, some of the state-of-the-art sensors actually use flux concentrators. So they do modify the field, but they modify it locally. So there is no really global modification of the field. With the electric field sensors, you have to be more careful, right? Because the sensor then will be at a certain level.
Well, if it acts like a ground plane or a mirror,
Yep.
then it's easy to solve the problem because you have two currents, one on each side.
For even voltages.
Yes, but I mean, if you have an electric field, it's like if you have two charges.
Right,
you
right,
can-
right, 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 right,
To the ground plane, then there's another charge on the other side. Then
right,
it's very
right,
easy to
right,
do all
right,
this.
right, 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 right. Okay. All right, so let me show you those two applications here and actually how we solved some of these problems in the real world. So the first one is non-intrusive circuit breaker monitoring, and Richard Su has been actually working on that extensively for about a year and a half now. And basically the idea there is that an easy way to sub-meter a dwelling like a home or a commercial setting would be to basically put these non-intrusive stick-on sensors onto the circuit breaker panel, right? And so here we have no galvanic connection with the circuit or with essentially the wires going through the circuit breakers or connecting to the circuit breakers. But we're essentially measuring the magnetic fields emanating from the breakers, and from there on back calculating what the currents are, right? So it allows for installment of these sensors without the need of an electrician. This is the example of our application. So here you can see these non-intrusive current sensors. They're all connected to a radio here, and the radio then remotely transmits the signal off from the system. On the left here, you can actually see the signal from two such sensors installed on the circuit breaker panel. And you can actually see here the signature of a light bulb, and then the space heater being turned on. So we've actually implemented this. I believe there is actually a system currently monitoring currents in Etcheverry Hall in this way. So, basically in 5 minutes, this can be installed. There is, of course, there are several advantages of the system. So in this case, the data, as you saw, goes through a radio to an access point, and then through the internet can be made available online. And so you can imagine if somebody installs this in their house, very quickly they can actually have remote access to their energy usage. If you're on vacation and maybe you have teenage children, you can quickly figure out, at night, is the energy usage going up? Is the stereo on full blast or things like that?
It's a good way to sub-meter cheaply, too, because often
Right.
you have dedicated devices that have its own circuit breaker, like a stove or a dryer or
Yep.
a washer.
Yep. And then, of course, later you can also use the signal from circuit breakers to, you can look for signatures in the signals from the individual circuit breakers to further sub-meter it even further down, right? Yes, go ahead.
It looks like the rise time on your data is pretty fast. Do you have a noise problem? Do you filter for noise at all?
No. So the bandwidth of, we have an RMS to DC converter, so some of the noise actually will be gone there. But the bandwidth of our sensor is actually the data collecting device here, this is through the internet, it's about 1 second. So as long as you get 1 second data, it's okay. And we do some averaging. Okay, so the sensors that we've used so far have been these electromechanical sensors. So essentially it's a cantilever beam with permanent magnets attached to it. And you actually have, we're inducing a mechanical motion of these magnets with respect to the current flowing into the individual circuits. And then we use piezoelectric coupling to actually get the voltage out from the mechanical motion. The nice thing about this is that the voltage here is actually substantial. And this circuit can also be used for energy harvesting. And so, the further down the application is that these sensors actually would be completely self-powered. You have sticky tabs that you just put on to the circuit breakers without the need for wires, and then they wirelessly transmit the information. But one of the other things we're also investigating is, application of solid-state AMR, TMR, giant magnetoresistive sensors, which have much higher bandwidth. These sensors are much more power hungry, but they have much higher bandwidth than this device. This is, this resonates at about 70 hertz, 60, 70 hertz. The bandwidth here, could be in the several kilohertz range. So that's something we're looking for further down the line to actually do signature detection from these circuit breakers. Now, the problem, like I mentioned before, is do we know? Yeah, sorry.
Is there any interest in measuring DC?
DC? DC. Right. I'm sure there is, maybe not in this application, but.
There's the application, the efforts to put in DC lighting.
Oh, I see what you're saying. Right.
There's a big effort to do the local PC in an office building.
Right.
You can still use the magnetic sensor to measure the field on DC, right?
Right, so especially this one, right?
This one is measure the grade.
Yeah, actually all of them would measure DC, yeah. Yeah.
Well, depending on what we've got in the beam, with the piezoelectric coupling, it's actually predominantly an AC device because, piezoelectric, if you're just putting DC on it, you're not going to get anything useful out of it. It all depends, you could change out the piezoelectric material there for piezo-resistant material or something similar, and then you could couple the DC, or one of the other sensing technologies, but the piezoelectric is AC primarily.
Or you could modulate it as well, right? And that would change it. Yeah. Okay, so one of the issues about, as I mentioned before, is the cross-coupling, right? So if we don't know the geometry of the wires within the circuit, then that becomes a problem. And so the whole point of installing these things onto a circuit breaker panel is basically that we can do this without removing the panel and looking what's behind it. So, this is an image that Richard actually found for the behind of a circuit breaker panel. You can see it looks quite ugly, right? And so we don't want to care about it. We don't want to know exactly where these wires go. So, so we've developed a deconvolution scheme, a calibration scheme and deconvolution scheme that allows us to actually get at it with a limited set of sensors without the need of performing a complete sensor scan here, a magnetic field scan. And the way it actually works is that we have a calibration load that is then being plugged into the individual outlets that correspond to the individual circuit breakers. And that load remotely, very quickly switches on, basically connects to the circuit, right, to create a known current, and then disconnects. And so we can see the relative change in that. And based on the relative change, we can then calculate these calibration coefficients right here. And so if we do that for all those circuits, we can actually construct the matrix, the calibration matrix, very quickly and figure out exactly what is the dependence of each of these sensors to each of the circuits. And once we have that, we can actually back calculate based on the sensors what is the current going through individual circuits. And then we actually tested this. So this is just data showing that works. We actually used this deconvolution scheme on a setup in our lab where we actually varied the background load, right? Because the idea is that you have some background load that you cannot disconnect. So there's always current flowing through these breakers. You're just adding a known load. What makes it a little bit complicated is that you could have, for example, reactive loads. You can have different power factors on these different circuit breakers. So the signal doesn't necessarily add up. You have to take into account the phase difference between these different currents. So, but that actually works very well, and so we are able to deconvolute the system, and this just shows the ground truth versus our deconvolution method on the test setup. So that concludes the application of the circuit breakers. Are there any questions about that at this point?
To what extent do you think you're measuring the field, the magnetic field caused by the current flowing through the conductor coming into the circuit breaker as opposed to the field caused by the solenoid coil inside inside the circuit breaker for the fast trip
Right.
mechanism?
So I think primarily we're measuring the field from the solenoid, actually, because there's a sweet spot on our circuit breaker where you can actually connect it. But there is also crosstalk to the solenoid next to you and so on, right? So we're picking up.
And I'd be particularly concerned about situations where you have adjacent solenoids that have 180-degree out-of-phase
Yeah.
currents flowing
Right.
through them.
Right.
And they would mutually cancel
Yep.
magnetic fields,
Yep.
and then what?
Exactly, but they will mutually cancel that in one point, right? One physical point. So as long as you're aware of that, you can then move your sensors in such a configuration that that doesn't become a problem. And so that's actually part of our method, is to figure out what is the best configuration space to locate these sensors. So basically what we can do is you have a sensor distribution, right? So the issue really becomes, is your matrix ill-conditioned, right? Do you have a degeneracy in your matrix, right? A point where you cannot distinguish between the 2 points. And so there's going to be some points into your configuration space where that is the case. But in such a case, you can actually figure out what would be the direction in which I have to move a sensor such that I minimize that degeneracy. Yeah. Mm-hmm.
Have you analyzed the matrix to see if there are some characteristics?
So we have looked at it some. We're in the process of actually sort of fully mapping the space out. But
Determinants or
right.
singular matrix?
Right, exactly, right. So one of the things, for example, you have to have, if you have, M circuits, you have to have at least N sensors to be able to decouple, so that the matrix is invertible, right? Yeah, right. And then the problem is there are going to be positions in the configuration space, like, for example, there is the symmetry line between two circuits that cross, right, where you're going to have this degeneracy, so you're actually going to have a singular matrix or close to singular matrix. And so then, but you can detect that, right? You can detect that condition, and you can say, okay, I really need to move that sensor away from that line. Yeah, that's a very good question. Okay, so the second application is in the domain of underground cable diagnostics. And so the idea here is that we have these underground cables. There are actually quite a lot of them, and specifically in residential areas where people prefer to have cables underground as opposed to having power lines above their head. Now these cables are degrading continuously and eventually failing. And they fail depending on a number of environmental conditions. Have there been submerged in water for a while? What is the acidity of that water? So it's difficult to determine just based on the lifetime of the cable when they are going to fail. And the question is, can we find methods to actually determine when these things fail? And the answer is yes, we can. We actually are working on this. We've been working on this for about almost 4 years now. Actually, I'm sorry, more than 4 years now. This is before my time here. But basically, the two ways an underground cable can fail is either the insulation in here can fail. This is actually a cross section of a cable. There's the conductor here. There's the insulation. So that insulation can fail. The cable shorts, and essentially there's a catastrophic failure of the cable. But then there's also the other failure mode. So on the outside of the cable, there's this conductive protective shield consisting of concentric neutral wires. And that shield can fail. It can actually corrode. These wires can corrode. And the primary goal of this shield is to conduct fault current back to the breaker that trips. Right? The problem is if that shield is corroded, the current is not conducted to the breaker doesn't trip. And so, for example, if somebody with a shovel digs into their backyard and crashes into the cable and cuts through the cable, the conductive path to the ground becomes the person holding the shovel as opposed to this. So this is really bad, and the utilities actually have to replace the cable if they know that this shield is gone. The question is, how do you detect that? In a three-phase balanced system, you're not going to have any current flow. You're really not going to see this, right? Until you actually have somebody with a shovel cutting into the cable. So we've actually been tasked on finding a way we can do to detect that. And the way we've actually done that, this is actually, before I go there, this is just a view sort of this whole diagnostic technique there is essentially, this is the cable, the elbows, and then we have sensors that we add onto this cable to actually perform the diagnostics. And also the key punchline there is we want to do this without disconnecting the cable from the line. So this is a live diagnostic technique. And so specifically for the concentric neutrals, what we have developed is a set of bracelets that are being strapped onto the cable. And they can actually perform a scan, a magnetic scan of the magnetic field emanating from the cable. And based on that look for currents flowing through these concentric neutrals, and then look for abnormalities, essentially irregularities in the current flowing, and detect the failed concentric neutrals from that. So again, it's a proximity-based technique. We're not coupling directly to the cable. We're just doing a magnetic field scan of the cable. So it's essentially the same concept. And so again, here, if you see the sorry? Yes?
If you have a concentric neutral wire with one break in it, you're grounded at each end, I would assume it's still safe. If you have two breaks in it, then that part is dangerous, which is floating. Is that correct or not?
Right. So, well, it's so the fault current is actually conducted through the entire system down. There is some connection to ground, but that's considered higher impedance. So you really want to have a sort of a concentric neutral that goes all the way back to your source, right? You don't want too much current to go through the ground. The fault can then occur anywhere in this concentric neutral, right? As long as you have some concentric neutrals that conduct, that's okay. But if there are, I believe it's if 25% of the neutrals are corroded, then there is, it's basically the maximum fault current is going to be such that there's going to be just too much impedance and it's going to trip the breaker. So the regulatory, I believe, is 25%. So 25% corroded, we have to replace the cable. Yeah. Okay, so basically we have these concentric neutrals distributed around this cable, right? And we're gonna try to determine when they are broken. The way we've done this is using off-the-shelf anisotropic magnetic field sensors, and the reason is that they are actually quite inexpensive. If you buy enough of them, they cost about $9, $10. And the nice thing is they actually perform a 3-axis measurement. So what we do when we do a magnetic field scan, we actually collect all 3 axes of the magnetic field emanating from the cable. And based on that, we can then, infer, do we have breaks, what's going on, do we see just a normal current flow. This is the fixture that we developed to actually test that concept. Again, in the field, and ultimately the idea is that this fixture is placed by a lineman, essentially when the cable is live, right? So there is a limited mobility issue. There's a hot stick that places the sensor. The person actually holding the hot stick has, this big electric gloves because the cable is energized at 12 kV. We're not there yet. So far, we created this fixture that can be snapped around the cable in our lab. So this is the cable. It contains a magnetic field sensor here. Then there is some circuitry, amplifiers, RMS to DC converters, and then a radio that actually sends this information to the unit where we actually perform the diagnostics. And then this can be rotated manually to perform the scan. And again, in the future, this will be automated. So these are some of the scans that we performed on our cable. Again, so what we're doing is we're measuring the magnetic field and trying to infer the current flow or in the circuit we're measuring, right? So we have the central conductor and we have the CNs. And so what's happening is these are the 3 axes of the magnetic field. You can actually see here the CNs are actually, so the concentric neutrals, when there is current returning through them, they're actually shielding the magnetic field emanating from the central conductor.
But the assumption here is that there's current flowing in the CN.
There is current flowing in the CN, yes. So we have to have current. So we're assuming there's going to be some imbalance, right, in the 3-phase configuration. Or maybe this is a single-phase feeder and we get actually 100% return. But there is some imbalance, some current flowing through the CNs. Yeah, correct. Yeah. Okay, and so then, we can actually detect this spike here, for example, in the magnetic field means this CN here is broken. And you can actually see, this is a signature of a failure. If there are more of them broken, like for example here, you can see there's also a clear signature of the failure here. And then we also see the signature of the failure in the other axis. So in the radial component, there's also this very nice dip and so this very nice signature. So that actually allows us to determine whether there's a break in the cable. Now, in this case, data is taken very close to where the break is done. So if you think about an underground distribution cable, we can access it at the ends. That's where the cable comes up, connects to a transformer, right? The failure could be anywhere in the cable. So this data is taken when the failure is very close. And this data here is taken when the failure is very far. So what's happening, you can still see the signature. However, there is a semiconductive shield around the cable as well to essentially smooth out the electric field around the concentric neutral wires. And so there is some re-entrance of the current through that conductive shield. So you can actually see there is this, this is a little bit maybe bad, but you see this peak here. That's actually a CN that's not there, right? That has a break, but some of the current is still flowing. But you can still see that signature right here. So we can actually detect it, even if the failure is in the middle, we can detect it from both ends of the cable. So this is 100% return. This is 50% return. Now the signal is lower, but you can still see a signature, a clear signature, right? However, it becomes more noisier, right? So then the problem is, we can see the signature, but it really helps to know where the CNs are. And so this goes back to when I was saying, do we know the configuration of that circuit or not, right? When we install this on an underground cable, we really don't, right? We're probing the cable. We can see the signature, but in these conditions where we actually have, little current, let's say below 50% CN return current flowing through the cable, the noise goes up. So it helps to know where the CNs are. And that's where we can actually use some active probing, right? So it goes back to the active probing idea I mentioned. So what we're going to have on the outcoming prototypes, this project actually is continuing. So on the next prototypes, we actually have a metal detector next to that sensor. And that metal detector will detect the location of the individual currents as you actually do scan. And so then we actually get the distribution of the CNs and the current flowing through them. And together that information allows us now to detect, is the current flowing through the CN, one CN and the other? And then if it isn't, what is there a break or not?
You're doing a measurement all around.
Mm-hmm.
So you have the Faraday law. So if you integrate the area under the curve, you should get the total current that goes through.
Mm-hmm. Mm-hmm.
So all those curves have the same current, or the difference
Yep.
means that they are less measured.
Right. The problem is, but there's going to be a contact resistance issue, right? So there's going to be differences in these currents as well, right?
Because of the flow.
Right. And then if there's a three-phase system,
Webcast. So when you have a question?
Could you repeat the question?
Right. So the question was, that's actually a good point. If the question was if Faraday's law, according to Faraday's law, we should be able to integrate the field around the cable, and then that should sum to the actually current flowing through the central conductor.
So those curves have.
Right. The problem is, so we haven't actually tested for that, but they should, right? In this case. In the field, the situation is going to be more complicated because you have a three-phase system, right? So you have to take care of all the phases. And the current returning through the CNs is going to actually be a convolution of all the three return of the phase imbalance and the phases in all the three phases going in, right? So, but if you take the entire system, yes, I mean, the current going in should match the current going out, right?
If I remember right, the Faraday's law is the scalar product. So it just all you have to do is run a circle, and that's it. It doesn't matter.
Right. But around the entire system, right? So around all the three cables.
Well, there you have one cable.
Right. So in this case, right.
So
but in the case,
you're running around the cable.
Yep.
And then if you do a scalar law and.
Yep.
scalar product, then you have the current that goes through.
Right. Right.
Which is, I think it's great because you need only a small sensor to rotate instead of having a bulky clamp, and put it around.
Right. Yeah, which is exactly what we have here. Right.
But I was expecting you were going to compute the area under the curve and say all these, are you getting that area that you say there 21.7 up from the integral or from the measurement of things going through the cable?
You mean right here?
Yeah. All of them should have the same areas.
Yeah. So you have to realize this is a magnetic field that we're scanning. We haven't converted it to current flowing through the system, right? But if we do, that's true, right?
Thank you.
Am I correct in thinking that there's a strong assumption that we're working with underground cables where the CN is a single layer of spiraled conductors that never touch each other?
Because that's a very good question, right.
A lot of the underground cables have two layers, one rotating clockwise, one rotating counterclockwise.
Right.
And so the currents will just jump back and forth.
Yeah, so a couple of things there. Yes, this is just one layer, right? We're not necessarily assuming they don't touch, but we're assuming that there is no current jumping across, right? That's correct. So the question is, as these things corrode, is there going to be a insulating layer between the CNs that will prevent the current? I mean, some of the current might leak, but is it what's going to be the least conductive path, right?
Or what was the original physical construction of the cable?
Right. Yeah. So some of the cables that actually are unjacketed, so jacketed cable, problem solved, right? Because the wires are embedded into the jacket. Some of the unjacketed cables that we've seen that actually have been taken out of the ground, they're surprisingly well ordered. So even though they're unjacketed, you don't have any bird caging, and the CNs still look pretty well separated. So, yeah. Are we 10 minutes? Okay. Good. Are there any other questions? Okay. So we've been there. It's unjacketed cable, right? So we did the test on unjacketed cables. And we could see essentially the same thing here. So the method works well on unjacketed cables. Again, the problem is if the CNs are touching, then that doesn't work. So this was the case where actually we have CNs that were not touching each other. So basically, this is my last slide, so we're good. So I would like to sort of bring it back to the whole concept of proximity-based sensing. And I think it's actually a very powerful technique because it allows us to embed sensors and into equipment without actually necessarily touching the circuits we're measuring. And looking at microfabricated sensors, really small, non-intrusive sensors that can be placed onto the equipment after the fact. This really allows for very rapid, inexpensive installation of this type of sensors. And allow us to perform diagnostics on equipment without the worry that we're going to somehow negatively impact the equipment that we're measuring, right? If we have to actually physically connect to that system, how knows how the cable will operate after that. So that's why I think it's a very powerful thing. And we're sort of almost just starting to scratch the surface, learning how essentially to do this interrogation of circuits remotely. So I foresee some very interesting applications in the energy space in the future. So I would like to acknowledge the students who work on this, and specifically Richard, Sue, and Chris Sherman, who are continuously right now pursuing this topic. And of course, our funding agencies that make this work possible. So that concludes my presentation. Thank you.
So we can have more questions for Igor? Okay.
Yes.
Hold on.
For the underground cable case, have the utility companies given you any guidelines for how far apart you can do your measurements or how close together you can do them?
Right. So they gave us a target spec of 300 feet. Right. So they would like to see us being able to detect a fault at 300 feet from the fault site. And we are able to do that.
Oh, you had the question.
The reliability of the measurements, I mean, is there any probability of, say, a false alarm detecting a breakage when there isn't any, and the vice versa?
Right, so far we've done this test in the lab, right, so in laboratory conditions. So, you know, we construct these faults essentially by just cutting through the CNs. We are in the process of doing we're starting to do a long time duration study. So actually performed in the winter and also in the spring. And that's where we actually will look for investigating, you know, what is the set of false positives, right? One thing we're worried about is contact resistance. So as these CNs are being corroded, they're actually, you know, there's corrosion from around them. And so there might be some CNs that actually are conducting, right? But because of the buildup of the corrosion at the interface, right? So the elbow comes up and connects to the transformator, right? Where it's actually, you know, grounded. They're not conducting much current, which might look like a fault here, right? But that's something that we haven't fully investigated yet, and that's essentially future work.
Sorry, but I have a question about that picture. So it's a bunch of ants making a bridge?
Mm-hmm.
Okay, so how do they get, there's a gap. How do they go into the gap? How do they get?
Yeah, so I basically just got this picture, but I think the ants started building the bridge here and they start pulling each other up and they add more ants here, right? So basically what's happening is we have a flat string of ants and they start climbing, and then they start adding more ants, right? And that's how we get the bridge.
This is why it's great to come to a university. It's a great question.
That's a very good question.
It's a catenary.
Yeah.
Signage or whatever.
Highly educated ants.
Yeah, so see, if we all work together, we can accomplish many interesting things, right? That's the punchline here.
So I don't have a question, but I have a comment.
Okay.
It's great what you're doing, and you're really tackling some very difficult problems that the state really needs. But what's interesting about your technology, from my perspective, is that there are a number of simpler problems that this technology will solve. So first of all, overhead distribution lines don't have the same inability to access the lines as you have underground. And so I can see that when you develop MEMS-type sensors of the type that you were showing, that 2 or 3 of them embedded in a structure around a clamp-on onto the lines should be able to be something that will be very worthwhile as smart grids need more information, as you know, on the distribution lines. And the second thing is Dick White always had started with the zip cord. And I expect that someday these same little MEMS sensors will get embedded in the head of power cords. Mm-hmm. And if they have their own radio, and if there's 2 or 3 of them, 1 or 2 can fail, and it still can give you a readout of what's actually going on in that appliance. So I think this work is extremely interesting in that you're solving very complex problems right now, but I think that as you develop these tools, the simpler problems are probably going to go to market much faster.
That's true. Yeah. Thank you.
Okay, looks like we have no more questions. Thank you, Igor.
Okay. Thank you.